Hello, everybody. So we'll talk about the fundamental theorem of algebra here. It's going to tie into polynomials and finding their complex solutions. So basically, the fundamental theorem of algebra itself is going to say if f of x is a polynomial of degree n, okay, and again, n has to be greater than 0, then f has at least one 0 in the complex number system. Okay, so that might not seem like it's telling you all that much. It's just saying it has at least one 0. But there's kind of like a next step, a little corollary of this that's basically going to say the number of complex zeros will actually equal the degree of the polynomial, which again we're calling n. So for example, if f of x is, I'll just make something up, 3x to the fifth plus 4x squared minus 200. Okay, so the degree is always just going to be the largest exponent. So this is a fifth degree polynomial. That means it would have 5 total zeros, okay, or 5 complex zeros. Some of them might be completely real numbers, okay, you'll see on the graph. Some of them may be completely imaginary or complex numbers where they're not going to show up on the graph. Okay, so just kind of keep an eye out. You kind of have an idea just by looking at the biggest exponent how many total zeros to expect. So let's walk through, find a couple here. Here is a polynomial when we want to find all the zeros of f of x equals x cubed minus 3x squared plus x plus 5. And we want to also write the polynomial as a factor of, as a product of linear factors. Okay, so when we're trying to find all zeros, kind of similar to quadratics, you can try and look at the function, see if it's factorable. Sometimes, maybe these things are factorable by grouping, and you can get the zeros that way. If that fails, then you're probably going to have to go to a graph in order to get a rational zero to then do some sort of division. Because the goal on these, again, is that this started as a third degree polynomial. We know if we can somehow divide it down into a quadratic, then we can always use the quadratic formula to find zeros. Okay, but sometimes just by graphing it, you will see the zeros all show up on the graph and they'll all be exact values, and you don't even have to do any algebra really. Okay, but this one, I do have a sketch of the graph here, and we can see there is one real zero showing up, okay, and it's a nice rational number at -1. So I know that x equals -1 is one of the zeros. Okay, and that kind of means then that x plus 1 is one of the factors. Okay, so our job is to just find the remaining zeros, and then we can find the factors as well. I know to expect 3 total zeros, okay, because that's the degree. So that means since we're not seeing the other two on the graph, they're going to be complex. One little tip about complex zeros, they always come in conjugate pairs. Okay, so like if you have a plus bi, you're always going to have a minus bi as well. Okay, so that seems to make sense. I'm seeing one. I know there's 2 missing, so it's probably some conjugate pair. So what we're going to do is take f of x, and we are going to divide it by the factor x plus 1. Okay, so I'm going to do that synthetically. So let's take, if we're dividing by x plus 1, we're going to use -1 in the box. Okay, so no, we actually use what the 0 actually is. And then synthetic division, since we are dividing by a linear binomial, we can use synthetic. Coefficients on f of x were 1x cubed, -3x squared, 1x, and then a constant of 5. Okay, and we are able to do the little synthetic process here. Hopefully we still remember how that works. We're going to bring down that 1, multiply by the -1 in the box, and then we're going to add straight down. So -3 and -1 is -4. -4 times -1 is 4. 1 plus the 4 is 5. And then 5 times -1 is -5. And just notice we do get, remember our synthetic substitution, that's telling me the y value is 0 when x is -1. And we knew that, right? That kind of just confirms that point. And we've done everything right so far. If you're not getting a 0 there, double check that you used the right number in the synthetic division box there. Okay, but what that tells us, we knew x plus 1 was a factor. Now the answer to the division problem is going to be x squared minus 4x plus 5. Okay, that is the other factor. Okay, so we can try to factor that. Again, since we were kind of expecting these other two zeros to be complex numbers, factoring may not work out. We may not be able to come up with factors of positive 5 that add up to negative 4. Okay, at least we can't do it using real numbers. But we can solve the equation always with the quadratic formula. Okay, so let's do that. We'll get our other zeros, and then we can then get the factors working backwards. All right, so quadratic formula is going to say x is going to be the opposite of b, plus or minus. We have the square root of b squared minus 4 times a times c, right, all over 2a. All right, we should be able to simplify that sum. Let's see what we can do there. 4 plus and minus, so underneath we have 16 minus 20, so negative 4, okay, all over 2. And then we can simplify a little bit further because we know the square root of negative 4 is 2i. So 4 plus and minus 2i over 2, which can go one final step here in dividing each coefficient by 2. The 4 over 2 is going to become 2, and the 2 over 2 is going to become just 1. So we're going to end up with 2 plus and minus I. Okay, so the zeros, let's just get a list of everything so we can answer the question clearly. The zeros are, again, we had x equals negative 1 from the graph. And then we just saw 2 plus and minus I. Okay, so remember that's two different things there. The plus and the minus are separate. And then that means that the factors, because this part of the question was to write the factors as well, the factors are just going to be the opposite. So x, instead of x equals negative 1, we'll write x plus 1. Okay, we will write, let me move this over a little bit. The other factors will be x minus 2 plus I, and finally x minus 2 minus I. Okay, so it's always just x minus whatever the zero happens to be. Okay, so that's going to be it. If we wanted to, we could kind of distribute those subtraction signs and just simplify this a little bit more, meaning x plus 1. This middle one, if we distributed the minus, would be x minus 2 minus I. And this last one, if we distributed the subtraction, would be x minus 2 and then plus I. Okay, so that'd probably be the best way to get everything simplified as much as possible. So that's the zeros and the factors of that polynomial. Example, where it crossed the x-intercept. See how it kind of crossed all the way through. When it came through negative 1 here, the graph crossed through the x-axis. Alright, so let's take a look at example 2 here. Kind of want to do the same thing, find all zeros of g of x equals all that stuff, and we want to write the polynomial as a product of linear factors. Okay, so again, factoring is probably not going to be simple, so I went right to a graph there. And on this graph, I wanted to point out, it appears at 2, 0, there is a 0 there, an x-intercept. Now it's only appearing to show 1, and I did zoom out the graph. It does not come back down and cross anywhere else. This is the only x-intercept. So the key here is, since this is a 4th degree polynomial, we know there's a total of 4 zeros. Okay, remember that the complex ones only show up in pairs. Okay, so there can't be just 3 of them. Okay, so that leads us to this idea of multiplicity and repeated roots. So if you take a look, if we go back to this one doesn't. This one just kind of comes down and touches it and goes right back up. Okay, and what that indicates is that this is going to be an even multiplicity, is the fancy word here, meaning that 0 is occurring an even number of times. Okay, so it might be like a double root. Okay, we might have x equals 2 twice, okay, or possibly all 4 of them. But in this case, I'm going to assume that it happens twice, okay, and I'm just going to say, I know that x equals 2 is a 0 from the graph. I'm assuming it has a multiplicity of 2 because, again, it's not crossing through the x-axis. The graph is kind of coming right back up. So here's the way we're going to know for sure. That means, again, that the factor, a factor is going to be x minus 2, but I think there might be another x minus 2. Okay, so what I'm going to do, I'm actually going to do synthetic division twice. divide by x minus 2, and then divide by x minus 2 again, and see what type of quadratic we get. Okay, because again, I know this originally was a 4th degree, so we're going to have to do synthetic division twice anyways to get it down to a quadratic. So let's just roll with it and let's see what happens and see what we get at the end, and see if that's going to give us two complex roots. So when we divide g of x by x minus 2, I'm going to use positive 2 in the box. My coefficients are 1 for the x to the 4th, negative 4x cubed, 8x squared, negative 16x's, and then positive 16 for the constant. Okay, and we'll do our synthetic process, bring the 1 down and multiply. Negative 4 and 2 is negative 2. Negative 2 times the 2 is negative 4. Okay, 4, 8, negative 8, negative 16. Okay, and we do get a 0 here. Okay, so right now, this is telling me when we divide it by x minus 2 once, we're getting 1x cubed minus 2x squared plus 4x minus 8. So what I'm going to do is divide by this factor again, okay, because it's a repeated factor. It's an even multiplicity. It shows up twice. So I'm going to do 2 again using these new coefficients. And at this step, the final answer will end up being a quadratic, okay, because again, remember now, once we get here, we're down to a 3rd degree. So we're dividing again to make it down to a 2nd degree. Okay, so we'll bring the 1 down and multiply. 0 times 2, 4 plus 0, and 4 times 2 is 8. Okay, and again, we are getting that 0 again. That's confirming that 2 was, there was another, it was a double root. Okay, but what we just got was x squared plus 4 is another factor. Okay, so far our factors are x squared plus 4, the x minus 2 twice, right? Okay. So what we need to do is figure out what are the other zeros. Okay, the other zeros come from solving x squared plus 4 equals 0. Okay, now you can do quadratic formula, just you know, using the a, b, and c. I'm actually going to solve this one just by taking square roots because there is no b value, there's no middle term in there. So if we just subtract 4 from both sides, x squared will equal negative 4, and that tells me x must equal plus or minus 2i. Okay, and then the factors, once you know the zeros, the factors that would come from those would be x minus 2i and x plus 2i, okay, along with the original x minus 2 and x minus 2. Oh, there we go. Okay, so these are all the factors. Okay, and all of the zeros are the plus or minus 2i along with negative 2. And we could just maybe note that it has a multiplicity of 2, or you could write it twice, either way. But that's it. That's the zeros. That's the factors. All right, one other thing we can do in this section, we can start out with being given the zeros and try to find the actual polynomial. So it's kind of working backwards, you know, like think of this like Jeopardy, right? You can, here's the answers, you find the equation. So if we know the zeros are at 2 and then 3 plus I, okay, one thing first, we know, remember those complex zeros always come in conjugate pairs. So if 3 plus I is a root, you automatically know that 3 minus I also needs to be added to the list. Okay, I think the books try to be sneaky and think that you'll forget that or whatever, but we're not going to forget that. All right, so we know we have 3 total zeros. Okay, so we should be able to get 3 linear factors, right, 1 for each. So I know that x minus 2 is a factor. I know that x minus, and be careful here, put these in parentheses, x minus 3 plus I, and x minus 3 minus I. Okay, those are the factors. Now to get our polynomial, we're just going to need to multiply those out. Okay, so let's first kind of simplify a little bit. Like we did before, let's distribute this minus sign in here. So x minus 3 minus I, and then x minus 3 plus I. So all I did there was kind of distribute the subtraction sign in each of these factors just so we could simplify a little bit. Okay, now what I want to do, I'm going to multiply these all together, but I'm going to do these two first, and then take their product times the x minus 2 at the end, just to I think it's just easier to multiply those first. So the x minus 2 is still there. Okay, let's multiply these guys. So it's a big distributing problem. So I'm gonna distribute the x times everything in the right parentheses. So x squared minus 3x plus x times I. Okay, now I will distribute the minus 3 to everything. So minus 3x plus 9 minus 3I. And then finally I'll distribute the minus I to everything. Minus ix plus 3I and minus I squared. Okay, so let's clean that one up a little bit. I'm just going to leave this x minus 2 alone for right now. If we start combining some terms and simplifying some things, so I see a plus xi minus xi, a minus 3i plus 3i. So that'll usually happen. All those i's are going to cancel out or be able to be simplified, meaning you probably have an I squared in there, but we know from before I squared is just negative 1. All right, so what we really have is x squared. There's minus 3x minus 3 more x, so minus 6x. And then there's a plus 9, and minus this negative 1 is really like minusing negative 1 is adding 1. So the plus 9 plus 1 is going to end up being a plus 10. Okay, so our final step will be now to multiply x minus 2 times x squared minus 6x plus 10. Okay, so let's distribute that x first. So x cubed minus 6x squared plus 10x. Okay, now we can distribute the minus 2. So minus 2x squared plus 12x minus 20. And if we combine these like terms, we will get our final answer of x cubed minus 6x squared minus 2 more, so minus 8x squared plus 10x plus 12x, so plus 22x and minus 20. Okay, so a lot of little steps. Just be extra careful, with distributing and combining like terms and in the parentheses, especially at the beginning. When you write those zeros at the beginning, if 3 plus I is a 0, make sure you're doing x minus that whole term in parentheses. Okay, same thing here. And then just be extra careful. Multiply it all out, and it should work out. It's not super easy to check these, but what you can do, you can graph that, okay? And you'll at least be able to verify that the one real 0 given should show up. Now this other one is, it's not going to show up on the graph. Be confident in the steps you did here. All right, so that is the fundamental theorem of algebra. Here's the graph of that function, and we can see that negative 2 does appear to be a 0, which is nice. It's just that the other one's being imaginary. You kind of just either have to solve this like we did in the first two examples, or just kind of